as kind of introduced, I guess as part of my role on the digital workflows group, I'm going to kind of canter very quickly through digital tools that are available really to all of us to use to really support us in our design process going forward. I thought I would start though with a warning. Look, really no digital tool, no bit of software, no really intelligent bit of software writing will really optimize a bad, terrible structural solution. And really what we all need to be doing, and really I hope I'm echoing the kind of thoughts that have already been put out there, that unless we do the basics right, then the software won't solve your problems. You cannot make a 100 meter spanning steel bridge low carbon. You can make it as low steel as you can, but it doesn't necessarily mean it's a low carbon design. And I think we just need to kind of, just hold that in our minds, that we really need to get the basics right. So what are those basics, as far as I'm concerned, really are about reducing spans, introducing stiffness through geometry. Every building I see at the moment is flat, 90-degree right angles. There's great work being done by university teams about creating vaulted concrete floors to reduce the amount of materials. With that, reducing the amount of elements we use in bending, optimizing our grids. And actually, we can do a lot of those things using widely available tools such as Grasshopper and Dynamo, which are plugins for 3D modeling software such as Rhino and Revit. And really what we want our digital tools to do is to allow us to prototype numerous different options and solutions to show us what the right answer is, or at least allow us to push the design team and the client towards a better answer. And those better answers are, as everybody has listed out through this presentations, are do nothing, all the way through to do as little as you can, down to then try and get the specification right. So I'm a big believer in choosing the right material for the job. I think nobody is naive enough to think that if the whole industry changed to building in timber tomorrow, there would be enough timber to supplement the whole world's design needs. So what we really need to get to a point is understanding which materials are the right materials for the right jobs. And really, I'm a massive fan of composite structures. We at Webb Yates have done a number of timber and concrete composites, as well as timber and stone. But steel and concrete and steel and timber are also viable options. And again, what we are trying to do is find options and use our software to hone the design down to meet the project parameters, often cost, often viability and availability of materials. So, I mean, just on that, I thought it wouldn't be a Webb Yates presentation, or a presentation from somebody from Webb Yates if we didn't throw in some pictures of some stone, but really thinking about what actual approaches we can take, which there may not be design tools that can allow you to design in stone. And at Webb Yates, we've developed all of our own software for doing these things. But timber and concrete composites is easily achievable within your own software, about looking at how you look at the interface shears between the two materials. So these things aren't beyond the kind of capability of most engineers in the industry. So what I want to do here, and there's going to be kind of a reasonable amount of information I'm going to put on the slide, and really I would just advocate that you come back and read through these and start looking at some of these links that are on the presentation. And what I'm doing is I'm really showing you where the free information is that you can all go and use and have a look at, and use these tools to really inform your design process. So there are a number of embodied carbon calculators that are available. Arup have one that's called the Pre-Designed Embodied Carbon Calculator. The Concrete Centre have a cost and carbon calculator, which I think is a paid for item. And that obviously covers concrete. Price and Myers have a really interesting tool called Panda, which really looks at multiple different structural forms and how you might optimize those. And it's a really interesting thing. So they called it Panda, and it's got some quite amusing Panda references in it. So I definitely suggest you go and have a look at that. And then IStructE and Elliott Wood have obviously developed the structural carbon tool, which is available to everybody. Now, I see these tools that I've just listed here as more of the early stage of design. where you can calculate volumes and plug those into those calculators for you to really let you know where are your designs at any point in time. But there are some what I would call later stage design tools, which are really linked to getting information predominantly out of Revit. And apologies that this is slightly Revit biased, but that seems to be the de facto modeling tool for most structural engineering firms. So one click LCA, actually you can use it to model all the carbon throughout a building, including a lot of the architectural and MEPs parts. There's E2 ELCD, the E2 Global, again, plugs into Revit, takes the data out, so you can parameterize carbon within Revit, or you can pump out the volumes and take those, put those through your software. And all it really requires is a basic understanding of how to allow you set up different parameters within Revit against your materials, and therefore allow your carbon calculators to do their thing. EOC have got their own, Ecclesly Callahan engineering practice in London have got their own Revit plugin, which is available for use. And then just at the bottom, for those who may not necessarily want to use proprietary tools that have been developed by other engineering practices and want to do it themselves, then the Autodesk University has put together a kind of guide on how to build your own carbon assessment tool for Revit, which predominantly uses Dynamo. And for those who kind of understand a little bit about sort of, digital workflows and digital design, Dynamo to Revit is the same as Grasshopper into Rhino. Okay, so I guess a little bit more information about all the various different routes you can go for optimization and using tools for optimization. And I think lots of the speakers today and the speakers later on will talk a lot about, various different parts of the design process. And really what I'm trying to illustrate here is just how difficult optimization is. And I think a lot of structural engineers feel that optimization is about, moving all of their steel section sizes to 99% utilizations, which of course is a certain type of optimization. But actually, there's so many different areas that you need to optimize. And sometimes the overall best carbon solution for a building isn't necessarily the lowest carbon for the structure, or it might not be the lowest carbon for the architecture. So what we need to get to a point of is having all of our various toolkits talk to each other, not just the structural engineers, but across the whole industry, so that decisions that are being made by one entity within the design team do not adversely affect others. And I've used the example before that if you do a timber floor, you use joists in a domestic property, you use timber joists and plywood flooring, and the structural engineer walks away thinking I've done my job. I've got a really lovely, warm, fluffy feeling about myself. But then the client wants underfloor heating in there, and then the builder then puts down a 3 mil thick aluminium plate across all of the timber floor, and all of a sudden we've introduced a whole load of energy and carbon in aluminium onto a floor, and maybe actually a concrete floor was the right answer. So it's really about using software to try and understand the kind of circular nature of design and how one decision that we make affects somebody else. And I think that's especially clear for structural engineers when we talk about thermal mass and how that affects the way you can passively heat and cool a building. Okay, so this is a chart actually you might see across numerous presentations that have been given by myself or my colleagues, but I think it really illustrates a really key point, that carbon is a parameter in the same way that weight and volume and strength is a parameter. And if it's a parameter, then we can parameterize it and we can use it in our design and we can get metrics out from it. And we use this slide really to just display why we would prefer not to be designing in primarily new structural steel, and obviously there'll be discussions later on about steel which is reused and brought back from recycled from a site rather than recycled and reformed into steel and then brought back. But really just to really demonstrate why steel is particularly bad, but also why timber is also quite good. But the difference in this change in design metric, that we have to think less about super slim columns and super slim floor plates and more really about what is the carbon impact of these decisions that we're making. In my opinion, if you have any doubt about how to optimize your structure, always optimize the lowest weight or lowest volume of material. So the use less will always get you to a point of your lowest carbon design. But it may not be the design that works with everybody else. And we have to be conscious of that. So BIM, I've kind of used, I mean, I'm not a massive fan of BIM, if I'm honest, but I've used this terminology in here, which is really about information. We need information to make our designs low carbon. And that's why we're here talking at these conferences. But it's also, you know, we should be taking this back to our own practices, looking at our back catalogue of projects and really understanding where are the wins. You know, shrinking all of your columns by 10 mil on all faces doesn't actually give you a huge carbon saving because it's not a huge volume. But potentially taking 25 mil off all of your slabs does. And the image on the right hand side, which is an output from the IStructE Elliott Wood calculator, really shows you where the predominant, where the large chunks of your carbon are. Really focus your efforts, because I think as engineers we can often go down sort of blind alleys and rabbit holes and get lost in this world of trying to optimize, and we spend a lot of time and unfortunately a lot of fee going down a route that doesn't necessarily give us huge gains. And really what we should be looking to do is take the information we have available to us, take the software we have available to us and the various toolkits to show us where to really spend our time and energy to efficiently and quickly pinpoint the real big wins that we can give to our clients, which are therefore cost effective. I'm just going to take a little moment to talk about a Webb Yates project, which is the Anna Freud Centre of Excellence, or also known as Cantor Centre of Excellence. This building is a timber frame, timber concrete composite frame. So we have timber frame, effectively joists at sort of 600 to 900 centres, as you can see in the photo on the left, and then we have a precast concrete slab on top. So I said at the very beginning, I'm a big believer in using materials for what they're good at and using the right material for the right job. So in this instance, the timber is doing what it's really good at. It's kind of working in bending. And the concrete's doing what it's good at, providing thermal mass, it's providing fire protection, and it's helping with the acoustics. So in this example, the concrete slab on this project is only 90 mil thick. So with the use less scenario, instead of, this could equally have been, 300 thick flat slab, I could have made a whole load of money and profit from doing that. And I could have walked down the road and been very happy that we'd pumped the whole thing full of GGBS and we've done a really good job. But no, we feel, or had felt with this, that if you went with a timber frame, used a composite action using coach bolts between the timber and the concrete slab, precast concrete slab, then you get a hugely optimized design where various elements of materials are doing the right job. And therefore we're in a situation where we've saved one building, because as part of this project we refurbished an adjacent building, we've built a new building next door to it, and in the new build element we've used as few sort of carbon damaging materials as we can. So great job us, well done, pat ourselves on the back. When we look at our carbon calculator for the job, and you will see that the precast elements and the timber frame elements make up 30 kilograms of CO2 per meter squared. And in my opinion, that is, based on current technology, that is about as carbon neutral as you can get for a structure, and it's exceptionally low. But we've got 171 kilograms of CO2 per square meter of in situ concrete. And you kind of scratch your head and say, well, what's that? That is a basement. So actually, going all the way back to the beginning of the design process, if we could have persuaded the client, persuaded the architect, the planners, that we shouldn't be building a basement in this location because of the impact on the carbon, then actually this building would have been a very, very low carbon building. And again, it goes back to those day one, stage two, RIBAJ stage two decisions where we're making these decisions, and in some cases bad decisions about having basements, which really do quite heavily impact the carbon. Unless we're looking at the information, unless we understand our projects and we're measuring these all the way through the process, we do not necessarily understand the net impact of our decision-making process. And these tools especially the early stage ones that I listed at the beginning, and then the later stage ones, which are really about trying to monitor your design going forward. These tools are essential in making sure that we make good decisions and we give good advice to our clients. So more sources of information. So there are a few data sources that can be used. The built environment carbon data source is one that's is about to go live in the next couple of months. And this is basically going to be the de facto place to get your carbon information from for materials and benchmarking for the UK construction sector. So as and when that goes live, I'm sure there will be a huge news announcement and there will be a follow-up in the IStructE to kind of promote it. But it's really making sure you guys are aware that this is there and it's coming up imminently. Along with that,
you have 1 minute, Tom. Sorry to interrupt.
That's all right. Along with that, we've got the UK Net Zero Building Standards, which is also coming out. And this, again, is about trying to get a benchmark where every project is measured on the same basis so that we get rid of all the kind of arguments and the Twitter spats that we keep seeing about whether a project really is or really isn't zero carbon. Finally, I've got 2 slides which I'm going to canter through really quickly. Circular economy track and trace. This is something I'm very interested in. I work on a lot of existing buildings where I don't have any data on the building. And I think going forward, if we can use items like Q code and we use a buildings database that is already used for building services to upload information for elements such as design life, paint specs, connection forces, etc., then in 25 years' time, when I'm retired and somebody else is looking at one of my buildings, they might be able to see what I've done, some of the design decisions, and they're not trying to track that information down. Despite various regulations about O&M manuals, you very rarely find the information you really require on existing buildings. And then finally, maybe in the future, we should be looking at really monitoring our buildings in use, putting strain gauges on the elements. We're about the only industry that makes something and walks away. We don't monitor it. We don't continue to look at something to see, did that building perform in the same manner as we expected and as we designed it to? And if we understood more about our buildings in use, maybe we could think about reducing loadings. Maybe we could think about reducing factors of safety. Maybe we could think about understanding if there has been an event occurred to a building, such as a terrorist incident, or maybe an overloading incident, does that mean that the whole building needs to be demolished, or actually can we save most of that building because we've got a time history analysis of the stresses within that building? And that's me done. Thank you very much.